You've seen this symbol probably a million times. It's everywhere. But that simple little equal sign has a surprisingly deep story, one that might just change the way you look at math forever. So let's get into it.
All right, to kick things off, take a look at this. Simple equation, right? What number do you think goes in that little box? Just take a second, think about it. You got an answer in your head?
Okay, so if you said 12, don't feel bad. You've just walked into a very, very common trap. A lot of us are taught from a young age to see the equal sign and think it means, and the answer is. So we do 8 plus 4, get 12, and pop it in the box. But that's not quite right. And it's a misunderstanding that can cause real headaches later on.
So let's fix that right now. To really get what the equal sign is about, we have to stop thinking of it as a button you press to get an answer. Instead, think of it like a perfectly balanced scale. This is the key right here. The equal sign is all about a relationship. It's making a very simple but very powerful claim. Whatever is on the left side has the exact same value as whatever is on the right side. That's it. It's a statement of sameness.
So let's go back to our little puzzle with this new idea. The left side, 8 plus 4, that's 12. So for this statement to be true, for the scale to be balanced, the right side also has to equal 12. And what plus 5 equals 12? Well, it has to be 7. Now it works. 12 on the left, 12 on the right. Perfect balance.
And you know, this goes all the way back to the guy who invented it. A Welsh mathematician named Robert Recorde came up with this symbol way back in the 1500s. And he chose two parallel lines because, as he put it, no two things can be more equal. The symbol itself is designed to shout, these two things are the same.
Now, once you really get this idea of balance, it totally changes how you see equations. They're not just problems you have to solve anymore. They become mathematical sentences, sentences that can either be true or false.
For instance, the statement 7 equals 7, well, that's a perfectly good sentence, and it happens to be true. But the statement 7 equals 8 is also a perfectly good sentence. It's just false. And realizing that you can write a correct mathematical sentence that isn't true is a huge step.
In fact, equations exist on this whole spectrum of truth. You've got statements that are always true, like x equals x. No matter what x is, that's true. Then you have statements that are never true, like x equals x plus 1. No number can be equal to 1 more than itself, right? But the really interesting ones, the ones that are the heart and soul of algebra, are the ones that are sometimes true.
And that is what it actually means to solve an equation. When a teacher gives you x plus 3 equals 7, you're not just finding an answer. You're on a quest to find the one and only value for x that makes that sometimes true statement into a right now, this is true statement. And of course, in this case, that magic number is 4. But, and here's where it gets really interesting, our familiar little symbol doesn't always play by these rules. It kind of has a secret identity. When it leaves the world of math and enters the world of computer programming, it's like it code switches. Just look at this. In math, a single equals means has the same value as. But in a ton of programming languages, a single equal sign is an action. It's a command. It means take the value on the right and assign it to the variable on the left. If you actually want to check if two things are equal, you have to use two equal signs. It's a totally different job.
And this right here is the perfect example. In math, x equals x plus 1 is impossible, right? It's nonsense. But in programming, you see this all the time. It's a series of instructions. It means, first, go find the current value of the variable x. Second, add 1 to it. And third, store that new result back in the variable x. It's a process, not a statement of truth.
Okay, so we've seen the equal sign in grade school and in computer code, but what about the really big leagues? Does the simple little idea of balance still matter when math gets incredibly complex? Let's find out.
Let's ask it plainly. Does this elegant concept of a balanced scale, of sameness, still hold up when you're dealing with the kind of math that describes the mind-bendingly complex shapes of our universe? So this beautiful, wild-looking thing is called a gyroid, and that monster of an equation is what describes it. I know, it looks terrifying, but just for a second, ignore all the sines and cosines and just look at the very, very end of it. What do you see?
Yep, it's just our old friend, the equal sign. And believe it or not, it means the exact same thing here as it did in our simple little puzzle from the beginning. This whole crazy equation is just asking a question. Find all of the points in 3D space, all the x, y, and z coordinates that make that entire expression on the left
perfectly balance out to 0. That's it. The core idea is exactly the same. So let's just recap. What have we learned? Number 1, the equal sign means is the same value as. It's about balance. Number 2, equations are just sentences that can be true, false, or sometimes true, and solving one just means you're finding what makes it true. And finally, while context is everything, like in programming, that fundamental idea of balance is what connects the simplest arithmetic to the most advanced ideas in science.
All of that packed into 2 tiny parallel lines. It really makes you stop and think, doesn't it? What other simple things do we see every single day that are hiding these incredible, complex worlds, just waiting for us to get curious?